we are from SMK Mentakab. Hi, I am Manusha.
And I am Lodisori.
We are here to conduct some experiments with lasers.
We will focus about reflection throughout the experiments. Hope you all enjoy the experiments. The experiments are laser waterfall,
Reflecting with a compact disc,
from laser spot to laser line,
reflecting laser on water surface.
The stimulated emission of light was a discovery by Einstein around 1916. All we need is an atom which possesses electrons just like any other atom in our world and a photon, that is, a quantum of light. The atom has electrons orbiting the atom's nucleus. For a better understanding, the Bohr model of the hydrogen atom will be used. The hydrogen atom has only one electron. The atom and the electron are on the ground state, namely E0. However, an electron may have other discrete values of energy. For this example, two energy levels will suffice, E1 and E2. An electron can be excited to a higher energy level by absorbing a photon whose energy is equal to the energy difference between the levels. The electron is said to be excited. However, after a very short time, the excited electron will go to the lower energy level by emitting a photon equal to the energy difference. This is called spontaneous emission. But when an atom absorbs a photon, and after a short time another photon is absorbed, a stimulated emission will be the result. The newly created photon has the same phase, frequency, polarization, and direction as the second photon. So it's a copy. The operation of lasers is based on the process of stimulated emission. Here we will discuss a three-energy level design. A photon is absorbed by the atom. The photon has enough energy to lift the electron from energy level E0 to energy level E2. Shortly afterwards, the electron jumps into energy level E1. This can occur without emission of a photon. A laser device is made up of several components. First of all, a mirror with a reflectivity of 100% is installed at one end of the device. Furthermore, we need a gas, a liquid or a solid that serves as the gain medium and creates identical photons. Another mirror with a reflectivity of about 98% must be installed at the other end of the gain medium. Another part we need is an energy source in order to use photons to raise electrons from a lower energy level to a higher one, a process called optical pumping. Now, let's have a look at the inside of the gain medium. The atom and the electron are on the ground state. Now, optical pumping, that is emitting energy in the form of photons, is used to raise the electron into a higher energy level. In this case, its energy level is E2. After a short period of time, the electron jumps into energy level E1 without emission of a photon. Consequently, the process of optical pumping cannot cause stimulated emission because there are two different amounts of energy present. The electron will maintain its energy level E1 for some time. Then, the atom will spontaneously emit a photon in a random direction as it relaxes to a lower electronic state. This photon may interact with an excited atom that hasn't emitted a photon yet. So, the photon hits the excited atom and causes a stimulated emission because the photon has the exact amount of energy to do that. Only photons emitted in a direction perpendicular to the mirrors will be reflected. The reflected photons initiate a chain reaction to produce more and more photons of the same kind. Furthermore, only photons with the same amount of energy and the same momentum will be part of the chain reaction. That's the reason why laser beams are strongly coherent and monochromatic. A very important aspect is the fact that many atoms must be in an excited state. For a laser to work, more atoms must be in an excited state than in lower energy states. This is called population inversion. The semi-transparent mirror allows some of the laser energy to be emitted while bouncing most of it back through the laser. There are many other.
Our first experiment is to test whether the light can be bended or not. For this, we would like to create the laser waterfall. In this experiment, technically the light does not bend. Observe the laminar flow water stream coming out of the bottle. When the water is in laminar flow, the water stream acts just like fiber optic and carries the light. When the light beam hits the water stream, the laser light gets reflected inside the stream. When light leaves a denser material, in this case water, due to the change in speed, it will change directions. However, when a certain angle called critical angle is reached, it reflects. Critical angle of water is 48.8 degrees. When the angle of the beam crosses the critical angle, the light does not go out of the stream and total internal reflection takes place. At the end of the stream, there is a lot of turbulence, so the continuous reflection chain breaks or scatters down and the laser light gets scattered. Because of this phenomenon called total internal reflection, the light appears to be traveling along with the water stream.
We now demonstrate total internal reflection of laser light in a water jet. A laser is aligned such that its light passes through a water tank and into a tube at the bottom of the tank. Powdered coffee cream has been added to the water to make the laser beam more visible. When the stopper is removed, water squirts out of the tank into the container below. The laser beam is reflected internally and follows the water jet into the tank. In this close-up view, we can see the internal reflections of the laser beam in the water jet.
Our second experiment is reflecting the laser beam on the surface of the compact disc. The surface of a compact disc is covered with concentric grooves, and when a laser beam shines on it, most of the light is reflected. However, the light that strikes the grooves is scattered in all directions. The light scattered from two of the grooves interferes constructively at only locations, which result in a diffraction pattern. The origin of this diffraction pattern is similar in concept to that produced from two slits. The locations of the regions of constructive interference can be determined by considering the difference in the path lengths between two beams of light that strike adjacent grooves on the disc. Our third experiment is making a laser line from a laser spot. Here we are using the cylindrical rod as the lens. When laser beam hit the cylindrical rod, the rod acts as the lens to spread out the beam or light into a line. As we can see here, we obtain a horizontal line when the glass rod is vertical, while we obtain a vertical line when the rod was placed horizontally. The cylindrical rod acts as the lens and refract the laser beam. As the result of the refraction, the laser spot changes into the laser line. Our fourth experiment is reflecting laser on water surface. When you shine light down onto water at any angle, the combined light force of the three beams incident, transmitted and reflected turns out to be entirely vertical. The horizontal force components cancel out, but when the light beam comes up through the water at an angle greater than about 49 degrees, it is almost all reflected back into the water. In this situation, it turns out that a horizontal force survives. The beam experiences a phase shift at the surface and a sideways shift of the incoming beam called the Gauss-Einstein effect, which provides the horizontal force. The net force pushes water from the edges of the beam toward its center, which could create a bump at the surface.
Light is reflected from the agent's particles as the beam passes through the water. And we're going to dim the lights so you can see what's happening. Next, I'm going to aim the laser down toward the water at an angle to see refraction in action. Look how the direction of the beam changes when it enters the water. Set the tank at the edge of the table and aim the beam upward to see refraction again. If you increase the angle of incidence by aiming the beam through the water from the side of the tank, you will observe total internal reflection. When a source of white light is sent through the tank, the light appears blue from the side because the short blue wavelengths are scattered more than any other. Looking through the end of the tank, the light appears to have a reddish tint because all of the blue wavelengths have been filtered out through scattering. You can also use diffraction gratings with different numbers of lines to observe interference patterns. Look at the well-defined maxima. There are so many characteristics to explore.